I'm going to be talking about the shape of things, or really how to organize space using algebra. So really my main goal for this talk, because I know there's a lot of different majors here, is I want to give you an idea about why someone might think about topology and what are some of the big questions that maybe someone who's active in research in topology would care about. So maybe the first thing that might come to mind is what is topology? So you could think of it as like the modern study of the shape of spaces, and it uses tools from a broad range of math disciplines. So also I want to say, if you have trouble reading my handwriting at any point, please let me know in the chat and I will rewrite something. iPads are a little hard to write clearly on. So topology uses a lot of different tools. You could go the more point set topology route, and then maybe that has to do a little more with analysis and get really hardcore into studying continuous maps or differentiable maps, things like that. There are algebraic methods, and in fact, a lot of the theorems that I'm going to tell you about today, the actual, if you look under the hood, the tools that are being used are algebraic methods, and there's other things too, like combinatorics. So there's lots of really interesting tools that go into studying topology. So it's the modern study of shape. And maybe the next question you might ask is, why would you bother thinking about shape in the first place? Like, that seems like a very rough thing to do. So what I want you to think about, imagine, like, I have this picture in front of me where you have 2 points. There's a blue point and there's a red point. And in both pictures, they're 3 kilometers apart. So in the first picture, I want you to think about, how would you figure out how long it would take to travel from the red point to the blue point if you were walking 6 kilometers an hour? So this, if you have a younger sibling who's like in elementary school or middle school, they could look at that and they could tell you, right? They would tell you that distance equals rate times time. And so time equals rate over distance. And then they would tell you that it would take you about half an hour to walk. But what about in the picture on the right? How long would that take you? The reason that we could calculate it in the first case is because we were just walking in a straight line. But if we're in a maze like this, well, first of all, maybe you turned the wrong way and you reach a dead end and you have to go back. But even if you took the absolute best path, the shortest possible path from the red point or blue point to the red point, you still wouldn't be able to calculate this easily. So here's the idea. How can how can you begin to understand distance in a space, or how to measure a space? So how to measure a space or move in a space, which is basically the study of geometry. Maybe you would call that geometry when you care about distances, if you don't know the shape of the space. So if you don't know its shape, which is topology. So maybe that's the motivating thing why you might think about stuff like this. So I told you there was an activity that I would like you to do to explore these kind of ideas. So if you missed the link that I posted in the chat, I'll post it again. You can either look at this screen. Oh, thank you. So you can either look at the screen or click that link, and I would like you to get into your groups. And I want you to think about, what is the shortest path for Pac-Man to take to get to his bicycle without running into any ghosts? So I'd like to open this up for y'all to have the opportunity to talk in the chat about what ideas you have. Did you have any thoughts on what you think the shortest path will be?
I guess my discussion, we first found a solution that you start left, then move up and around the little box in the center as one valid solution.
Okay, and that's shorter than all of the other paths? So there's one idea. I like it.
I think our group and also the people in chat, yeah, up and to the right through like that.
Okay.
Yeah.
Was what we came up with.
Great. I think if you count it out, if you sort of treat every little box as distance 1, then I think the pink path is slightly shorter. But what I want you to take away from this is that you notice that on this Pac-Man world, Pac-Man can go out the right and come back through the left. And so really, let's think about, so I'm going to say that the answer for this question, you can check for yourself, it should be through the side. And the point is, why does that work? Well, it turns out that the Pac-Man world map is actually not, it actually has some non-trivial shape to it. You should think about this as, so think about the world map as having the right side glued to the left side. That's what it really means when we say that Pac-Man can, go out this way and somehow come back this way. That really the picture that we're looking at is this crudely drawn cylinder that I have here. This pink path actually was like going around the back of the cylinder. So you have intuitively been thinking about the topology of a space when you're solving problems in Pac-Man before, if you played Pac-Man before, right? But maybe you weren't thinking about it in topological terms. Are there any questions so far? Okay, so hopefully you at least are open to the idea that knowing about the shape of a space is important if you want to sort of do anything in the space, even, basic things like how long things take, how far things are apart. So the next question you might ask is, when are spaces the same shape? So here on the left, here's a sphere. Maybe, especially since there are lots of scientists here, maybe you could think if you zoomed in really close, maybe that sphere actually looks pretty bad, right? Maybe we're just zoomed out far enough that it looks nice. So what you might want to think is, when is a sphere still a sphere? And I'm going to say, for topologists, if we're considering things being the same, cool. We just saw in the chat y'all talking about Zelda fan games using novel topologies. That's great. Right. So we want to think about, when are two spaces the same shape? And for us, I want to think about this thing on the right as also still being a sphere. So still a sphere. Okay, maybe I've drawn it really badly. Maybe if you tried to do some geometry on it, like if you've taken multivariable calculus and you want to calculate the curvature, they would have, slightly different curvatures, things like that. But as far as, can we look at it and think whoever drew this was trying to draw a sphere or not? We're going to consider these as the same. So there's a few different notions of same in the topology world. So a few different notions. So a few different notions of same, but I think for our purposes, maybe we'll just say intuitively. Intuitively, we'll think about same as can smoothly deform one to the other. So can smoothly deform one to the other. If you want to know some more precise things, maybe talk to Dr. Bosman after. Okay, so using this kind of idea, how would you tell if spaces are different in the first place, right? So, geometry is not going to work. Volume, you can have two things be spheres and have different volumes. So you need something else. So here's two pictures. Here's these strips. The one on the left has a full twist in it. The one on the right has a half twist in it. And what you can check for yourself is that the one on the left has two sides. I color them for you. Two sides, green and blue. And the one on the right actually mysteriously only has one side. So even though both of those strips you could stretch, you could bend them in weird ways, no matter how you stretch or bend or shrink or whatever you want, the thing on the left has two sides and the thing on the right has one side. So this is an example of something called an invariant. If a property or quantity is the same for two spaces, which are topologically the same. We say it is a topological invariant, the property or quantity that is. So we say it is a topological invariant. So we've already seen one now. We've already seen an example of a topological invariant. So number of sides is one. So number of sides of a surface is an invariant. So here's another example of a surface that just has one side, or an object that just has one side. It's kind of fun to think about. Maybe you've seen it before at Klein bottle. Maybe you recognize this thing on the right on the previous column. This is a Mobius band. And maybe here's a fun exercise or fun fact. Just write it as it's fun, that a Klein bottle is two Mobius bands glued together along their edge. So it's a fun thing to think about. Are there any questions so far? Okay, so let's take an inventory of what we've done. We understand why, shape is important. We know that it's kind of difficult to tell when things are the same shape, but if we have some sort of invariant, then maybe we can use it to at least tell when shapes are different. So now maybe the next natural thing to think about, oh, hold on, sorry, for some reason it's not scrolling here. So now maybe the next thing you might think is, what are all possible shapes? Right? That's, we're following our mathematical nose and thinking, okay, well, what's possible then? So this is too big of a question. This is too big. So just like when we're doing math that's maybe less high level, maybe when you're doing calculus, what you should think is, if you have too big of a question, we need to break it up into smaller pieces. So break it up into smaller pieces. So let's think about this one dimension at a time. So in order to do that, let's remind ourselves what it means to live in a certain dimensional shape, or what does it mean for a space to be a certain dimension. So remember, for those of you who have taken linear algebra, that is maybe something to have in the back of your mind, is what did dimension mean in linear algebra? But for now, maybe you don't have to have taken linear algebra to understand what's going on. So let's look at one-dimensional shapes. I want you to think about a bug on a wire. So here, I have drawn for you, using the magic of clip art, a bug on a wire. And I want to convince you that this is a one-dimensional object, that the wire is a one-dimensional object. So you might immediately think, well, I can look at a bug on a wire. It exists in three-dimensional space. That's not one-dimensional. But I want you to think about, if you were living on the wire, what would the world look like to you? And the point is that the wire itself is one-dimensional because there's only one direction you can move in. Now, maybe I want to see some answers in the chat. And there's a really great question I want to address in a minute, but I want to see some answers in the chat. Why am I calling this one direction to move in? Because the ladybug can move forwards or backwards. Why am I calling that one direction? Using some vector space language. Love it. Love it. So what you should think about is, this is like moving, it's like moving this backwards is just negative forward. It's like changing the scalar. So there's one dimension to move in, and you can move in it positively or negatively. So positive direction, negative direction, or negative, but in the same direction. So great. Before we continue to the next dimension, I want to answer this question from Noah, which is, are there cases where a topological invariant doesn't change across different shapes? Yeah, certainly, unless you have a complete invariant. In fact, it's usually common for two different shapes to have the same value of an invariant. And that's why it's important to have a lot of different topological invariants that you use for different things. And in fact, we actually just saw an example of this before. The Mobius band has number of sides is a topological invariant. Mobius band has one side. Klein-Bottle also has one side. So just number of sides is not going to tell the difference between a Mobius band and a Klein-Bottle. So you need something more. Maybe number of edges is also a topological invariant. Mobius band has one side, one edge. Klein-Bottle has one side, no edges. So you needed a new one to tell the difference. Yeah, great question. Great question. Okay, so great. One-dimensional shapes. You have one dimension or one direction, you can move positive or negatively in. So now let's think about two-dimensional shapes. And again, maybe this picture that I have is making you really uncomfortable because it looks like this is a ball that looks like you need 3 dimensions. There's a car on it. But what I want you to think about is if you are sitting in the car, you are on the ball itself. Maybe imagine the ball is like a hollow metal shell, like a hollow magnetic shell, and this is a little metal car just driving around on it. You need to think about what it looks like for the car. And the point is that that is two-dimensional. You have two directions to move in, and that could be positively or negatively. And here they are. You can move this way positively or negatively, and this way positively or negatively, and that will get you to any point on the sphere. Okay. So you can keep going with this, three-dimensional shapes, same kind of idea. You could think about this bird in 3 space, and hopefully at least this one is a little more comfortable to you. We have 3 dimensions, then we have 3 directions to move in. And we'll stop there for now. So remember, why are we talking about this? We want to classify all possible shapes, and we want to break it down by dimension. So it turns out what we know is that in one dimension, or for one-dimensional shapes, at least ones that are sort of nice, in some technical sense we're not really going to talk about as much, the only things that can happen that are one-dimensional are collections of circles and line segments. And in case you're uncomfortable with the idea that I haven't really talked about anything infinite, I'm going to say we're going to stick to things that are finite today. So collections of circles and line segments. And that's it. This is actually a really good exercise to think about for yourself. So 2 dimensions actually gets much harder, but thanks to work of Dane and Haygaard in, let's see, Dane, Haygaard, 1907, and Radeau in, I think, 25, all 2-dimensional shapes look like either a sphere. So this is hollow, right? If we're thinking 2 dimensions, it better be hollow. They look like spheres. They look like hollow donuts, or they can look like hollow donuts with a lot of holes. Maybe let's restrict this. I didn't really talk about orientation. I want to be I want to be precise enough that people aren't upset, but also not distract from the main point. So maybe let's stick to things that have one side. That's another word for that is orientable. And the point is that surfaces, two-dimensional shapes, they all kind of look like hollow donuts or hollow donuts with a lot of holes. Okay. So what about 3D? So this is a much harder question. So this is a much harder question. So we need a little more technical language. So an N manifold, intuitively, is a space that, actually meant to switch these. Editing in real time. Okay, great. So what I want you to understand is that we say that a space is n-dimensional if it has n degrees of freedom or directions you can move in while you're sitting in it. So we saw that before. That's why we call a line one-dimensional. We call this a sphere, a hollow sphere, two-dimensional, and so on. So the simplest possible n-dimensional shape is called n-dimensional Euclidean space, and it's denoted Rn. So just like this picture where I drew the bird here, that's really an R3, which you spent some time in multivariable calculus exploring. But you can think about Rn. So an n-dimensional manifold, which is really what we've been meaning when we say a nice space, is a space that locally looks like Rn with some technical conditions on how the local pictures intersect. So to give you a feel for why we would define it this way, I want to come back to this Pac-Man example that we did before. So if you're Pac-Man, if you look really close, like let's maybe assume that Pac-Man can't see very far, but I mean, I guess even if he could, there's walls in the way. Point is, to Pac-Man, it looks like Pac-Man is just in a flat plane, right? Pac-Man can't see that secretly he's on a cylinder, right? But we can zoom out. We can look at this map and understand that he's actually sitting on a cylinder. So this is the idea of a manifold, that locally it looks like everything is simple, everything is nice, but if we zoom out more, we actually see that there's some interesting shape stuff going on. Are there any questions so far? Thanks, Dr. Bosman, for responding in the chat to Nicholas's question. Awesome. Awesome. So as I said, the case for 3D is a much harder question. I want to give you a couple of examples. So there's a couple of questions involving something having an edge, and I promise we'll get to that in like 10 minutes. You're right that we're kind of, I'm obscuring a couple of things here. Maybe I'll say for surfaces, anything with an edge is going to look like one of these donuts, but with like a disc cut out. Something like that. Absolute wonderful question. So you could have things like, that. Yeah, or even like a plate. I think a couple people said that. Okay, great. All right, so here's a couple of other examples just for other ends. So a zero manifold is just a collection of points, because R0 is just the single point at the origin. These surfaces we've been drawing, these are examples of two manifolds. This is the language that we would use. Here's a two manifold. So the classification of three manifolds, that didn't happen until the 80s. And it was the result of over 50 years of development using extremely difficult algebra and geometry. So this becomes a very hard question very, very quickly. The exact statement is beyond the scope of this talk, but if you're interested in the topological version, you could look up the JSJ decomposition of a three manifold. And if you're interested in a little more geometry, you can look up the geometrization conjecture and some things about that. So this is a pretty difficult question. But maybe the next thing is, you know, this got hard really fast. What about all the other dimensions? Well, it turns out there's this very cool and maybe very frustrating, depending on your perspective, theorem of Markov from the 60s that says that it is not possible to classify manifolds of dimension 4 and higher using our current notion of same. And for the experts in the audience, maybe I'll say the notion of same we've been doing this whole time was homeomorphism. If you don't already know what that is, don't worry about it. Just think, you know, squishing without cutting or, you know, creasing or whatever. Okay, great. So this theorem, really big, really cool, also really frustrating, means we can't really just keep going dimension by dimension. So what happens instead if we loosen our definition of same? So what is the appropriate definition of same to get us, great question, that's where we're going, right? Yeah, so what is the appropriate definition of same to get us something we can actually classify, right? Because that theorem of Markov just told us we actually can't classify manifolds of dimension 4 and higher using this kind of stuff. So I want you to think about exactly the stuff that people have been talking about in the chat, which has been really wonderful, which is that a manifold has boundary if it has an edge. And it turns out that the boundary of an n+1 manifold is always an n manifold. So in this picture right here, this is a 2 manifold. And I'm going to abbreviate manifold as MFD. So this is a 2 manifold with boundary. And it's no coincidence that its boundary is a 1 manifold, which is just a circle. And if you're having trouble deciding whether a manifold has boundary or not, if you're trying to figure this out, think about what would happen if you were, standing on it. If you were standing on the manifold and you were walking around, would you eventually get to a point where you would fall off, right? If you walk right up to that magenta circle, you would either fall off, or if you were somehow wearing magnetic shoes, you would flip over to the other side, like inside, right? But something changes when you get up to there. Sorry if there's background noise. I guess there's a lawnmower outside. Okay, so here's a 2 manifold with boundary, 1 manifold. Next to it, maybe this is a little harder to see. This is a 3 manifold. And here you're starting to see the limitations of 2D representations of 3D things. But this is a 3 manifold, a ball, with boundary, a 2 manifold. So with boundary, a 2 manifold, a sphere. And if you want to picture this and try to understand why that's an edge, had a boundary around 2 of the genus. Yeah, you could do something like that if you had like a genus 2 surface and then cut a disk out of the back. That's kind of like going around 2. Yeah. Okay. Anyway, right. So I was trying to see how you can imagine this sphere as a boundary of a ball. Imagine you're like a little bird, and I can't really draw, so I'm going to say, hopefully you can suspend your disbelief and imagine that this is a bird, or maybe some sort of trapped pterodactyl. I don't know. Imagine your bird flying around in a spherical cage. Imagine that sphere as like the cage that the bird is flying in, right? The bird can fly around anywhere inside the ball, and if it reaches that edge of the cage, then it can't get out. So that's like the boundary of a 3 manifold. So this leads us to another definition, which is that 2 n manifolds, and I'm going to call them, maybe I'm going to use a consistent color scheme this whole time because I think it'll be easier. And I'm going to use blue and orange just because I know a lot of people are colorblind and I think that's easier to see. But if for some reason you're having trouble with colors, let me know and I'll change the color of something. So 2 n manifolds, M and N, are cobordant. So cobordant if together they form the boundary of an n+1 manifold, and maybe we'll call it C. So I want to give you, I mean, it's important. Lots of people are colorblind. Right. Okay. So, right. So I think the best way to understand cobordisms is to just look at some examples of them. So I want to show you some examples of them on the right. So this first one, maybe it's a little hard to see that it's a cobordism because you're not used to thinking about 0-dimensional things, but these orange 2 dots, that's a 0 manifold. There's 2 points. These blue 2 dots, that's also a 0 manifold. That's 2 points. And look what's connecting them. Hopefully that lawnmower isn't as loud for y'all as it is for me. I'm sorry. Okay. So the cobordism C is a 1 manifold, even though it's in 2 pieces. I understand that might be uncomfortable, but it's still a single 1 manifold that goes from the orange 0 manifold to the blue 0 manifold. So this is a cobordism between N and M. how do I want to label this? Maybe I'll say this is a one-dimensional cobordism between zero manifolds. Okay, now bump one dimension up and that Y thing is a similar idea. That Y thing over there, this is a cobordism between two one manifolds. Single circle, so remember we said that all one-dimensional, now we can call them manifolds, because that's what we were doing this whole time. One manifolds are collections of circles and line segments. So maybe there's like a technical thing that the boundary of a manifold with boundary can't itself have boundary. So if you're like wondering why they have to be circles and not line segments, think for yourself about why that's actually not really topologically possible. Okay, so one manifolds, collections of circles. And here we go. M is a single circle. Lawnmower stopped. Great. Okay, N is two circles. And then we have this cobordism in the middle. If you think about it, it's like a cylinder that sort of comes off in two pieces. So this is a two-dimensional cobordism between one manifolds. And finally, here's the maybe hardest one to understand, which is this thing on the bottom. I promise you this is a 3D cobordism between 2D manifolds. It's a little difficult to see. So maybe let's think about our first manifold M as being this three-hole donut on the outside. If you want to think about this as like a cage for a bird or some sort of really bizarre aquarium for a fish, you can think about it that way, to think about, you know, the inside of it. So the outside is M. You can think of that as filled in, and then think about this thing on the inside is like drilled out of it. So here's the other side of this three manifold. This N is inside. So this is a 3D cobordism between two manifolds. So are there any questions so far? Okay, so what I want you to take away from this is that this is another notion of equivalence, instead of what we were using before. So maybe a little bit of foreshadowing is that we will be able to classify N manifolds up to this type of equivalence, and we won't just get a set. So I want to remind you, because I did promise you some algebra, this is where the algebra is going to come in. I want to remind you that there's this algebraic structure called a group. So maybe, you know, I don't want to teach you all of the first couple of lectures of a group theory class in colloquium, because that's a little too much, but I'm going to show you for an example, like what the structure might look like. So maybe the example we should have in the back of our minds is Z. And for those who haven't seen this before, Z is shorthand for the integers, the set of integers. Mathematicians often use this language. So as an example, I want you to think about integers with addition. So a group is a set. It better have a binary operation that takes two elements in the set and returns a third element. So for integers, if you take an integer n and an integer m, then that definitely gives you an integer back. So satisfies the first thing. A group better have an identity such that any element A in your group better if you add that identity to it, it gives you the original element back. Also, for those in the know, if you are upset that I'm using plus instead of dot, this is intentional. I hear you, I see you. We're still gonna stick with plus. Okay, so n plus m is an integer identity. The identity element for the integers is 0, right? Any integer plus 0 is equal to itself. So check. And then finally, the last thing that a group better have is for every element A and G, there is an inverse element negative A and G, so that A plus negative A is equal to your identity. So for integers, if you have an integer n, then if you add -1 times n to that, you get 0. So check. These are the things that we need for a group. Maybe on your own time, you could think about and this is why I have that clock up here, the fact that the numbers on a clock with addition is also a group. Numbers on a clock with addition, that's also a group. Okay. Are there any questions so far? I love this question. How some different or similar are groups to vector spaces? That's great. So actually, technically, every vector space is a group with some additional structure, but it's the same kind of idea that like you have some sort of general algebraic structure like a vector space, you prove things about that, and then anytime you encounter that same kind of structure again, you already know all these facts about it. Love it. It's really great. Okay, so I mention this because it turns out that if you think about manifolds up to cobordism as same, then you actually do get a group. So we want a group structure on manifolds. So maybe your first question should be, how do you combine manifolds in the first place? Well, there's this actually really natural binary operation that's disjoint union. So for two n manifolds, m and n, the disjoint union, which we'll denote like this, like a little square cup, that is the manifold with m and n as disjoint components. So it's literally just stick them next to each other, call it a day. Here's an example. This is the disjoint union of a genus 2 surface. It's what we call the donut with two holes. Genus is number of holes. Genus 2 surface and a sphere. And that's a great question, and we'll actually get to that in a minute. Yasser, you should think about, if you take the disjoint union with a sphere, something has changed. You have an extra sphere in your manifold. So we'll get to that, but I love how you're thinking. Okay, great. So binary operation, take your two things, stick them next to each other, call it a day. What about inverses? So we've really not talked about orientation too much. I'm going to mention it briefly to give you an idea because we do need it for inverses. Orientation is kind of like a choice of positive side, like for a surface, choice of positive side, choice of negative side. For higher dimensional things, if you've taken Cal 3 or multi, I'm not sure what you call it at Andrews, you can think about it that way. If you have a right-handed coordinate system or a left-handed coordinate system, it's a choice of which one is the positive one, okay? So let M be a manifold with a chosen orientation. Negative M is the same underlying manifold with the other one. So here's an example. If you think about, maybe let's color this. I want to keep the same direction I did before. If you orient this line segment as going from the orange point to the blue point, then that same manifold with the opposite orientation would have the line instead going from the blue to the orange. So here's something you want to try at home, kind of a fun exercise. For any manifold M, the result of gluing the interval 0, 1 to every single point of M, which for those in the know, we'd call that M cross 0, 1, or the product of M with the interval. That thing has boundary M disjoint union minus M. So we should think about this, maybe the takeaway. So takeaway is that M disjoint union minus M is cobordant. So that's the word we use when we say there is a cobordism between them, is cobordant to the empty set. So this actually comes back to Yasser's question. So what have we just seen? The set of n manifolds where M and n are the same if they are cobordant, or if there's a cobordism between them, has a binary operation, which is disjoint union. It takes two manifolds of the same dimension, returns a third one. It has an identity manifold, which is just the empty set or the empty manifold, where M disjoint union empty just equals M. So as before, like that exercise that I said I want you to think about on your own, M and minus M always bound a simple n+1 manifold that's just, you take M and you glue an interval to every point. We can think about this as a cobordism from M disjoint union minus M to the empty manifold. So that means that M has itself with the opposite orientation as its inverse. So this was developed in 1895 by Poincaré. And maybe, as you might expect from the discussion so far, this is a group. So this is denoted omega n. And we call this the n-dimensional cobordism group. Some people just call it the boardism group. They don't say the co. So this is n-dimensional cobordism group. And this is just the set of n-dimensional manifolds up to cobordism with disjoint union as the operation. And what I want to tell you is that these groups can be completely classified. It's taken a lot of work. It's been almost 100 years of work to classify all of them, but this we can actually do for every dimension. So I'm just going to tell you about some of the lower ones so I can get to where I come into this research. And actually, Dr. Bosman does similar research to me, so this also kind of tells you where he fits in too. But I want to remind you that we say that two groups are isomorphic. So G and H, they're isomorphic if there is a one-to-one onto function where, I guess I wrote plus, so I should write plus again here. If there's a one-to-one onto function that preserves the group operation, preserves the binary operation. So like phi of G1 plus G2 better be phi of G1 plus phi of G2. And if you like the analogy to vector spaces, you could think about this as being a linear map, but for whatever group that you're in. So one thing you can try at home, here's another fun thing to prove for yourself, is that omega 0 is Z. That one you can sort of draw out, but the other ones are a little more difficult. So here's some theorems. And I want you to pay attention to the dates on these to understand how difficult this is to do. So omega 1, remember that's one manifolds, which are, so one manifolds, those are just collections of circles, right? So this is actually isomorphic to the trivial group. And maybe I'll just say a word about why. So this is the trivial group. It has one element, it just has the identity. And this is because if you think about every one manifold, so every one manifold is some collection of circles. But any collection of circles, you can fill in. So if you think about it, this is just a cobordism to the empty set or the empty manifold. So if you can fill in everything, then that means that that group is just trivial. There's nothing other than the identity. Okay. Omega 2, unfortunately, is also trivial. So maybe this might start worrying you. Maybe we took the wrong notion of same yet again, but I promise we're getting somewhere here. So omega 2, this is trivial. Maybe just roughly what you should think is that every multi-hole donut can be filled in, or every multi-hole donut shell can be filled in with an actual donut. So think about it that way, okay? So here things get more difficult. The omega 3, this is also trivial. Oh no, this was much harder to prove. So this was by Rockleen in 1951. And what he showed is that every 3 manifold is the boundary of a 4 manifold. This is a pretty deep theorem, so this is pretty difficult. So why am I showing you this? Is this ever non-zero? It turns out that omega 4, so remember this is 4 manifolds up to cobordism. This is actually isomorphic to the integers, and this was proven by Tom, I think in 1952. And I want to stop here with this, but maybe I'll say, as an aside, you can look up on Wikipedia, you can actually classify all of them. I want to stop at 4 because I want to take inventory of what we've learned. What we've learned so far is that the 4th dimension is weird. If you remember from like 30, 40 minutes ago, and I know we're about out of time, I promise, I just have a couple of things more to tell you. If you remember from a few minutes ago, we said that this theorem of Markov said that starting at dimension 4, we can't classify manifolds up to homeomorphism. Now we're looking at cobordism, and it's all trivial. 1, 2, 3, that's trivial until we get to 4, and now suddenly there's this Z. Okay, so what you should think is that means that the 4th dimension is strange. The 4th dimension is where things start changing. Okay, so maybe your next question might be, did we simplify things too much? And so this is where Dr. Bosman and I come in. And what I want you to think about is what happens if we look at cobordism groups of lower dimensional manifolds sitting inside higher dimensional manifolds. So for things, for reasons that are maybe beyond the scope of a talk like this, the maybe first thing you should think about if you want to do an idea like this, thinking about lower dimensional manifolds sitting inside another one and some sort of cobordism going on, you should think about one manifolds in R3. So if you've seen Dr. Bosman talk about his research before, maybe you've heard these words that a knot in R3 is a smooth embedding of a circle into 3 space. And an n component link is a smooth embedding of n disjoint circles into 3 space. And even better, every link corresponds to a 3 manifold using something called Dane surgery, and a 4 manifold through something called handle attachment. So even though it seems weird that maybe we're studying these 1 manifolds sitting in R3, what does that have to do with anything? It turns out that there are deep relationships between this and the way 3 and 4 manifolds can be related to each other. So maybe the last thing that I want to leave you with, because I know we're about out of time, is that if 2 knots in R3 are cobordant by a cylinder, so not just any cobordism, not like that Y that we had before, but an actual cylinder in R3 times the interval, we say they are concordant. So it's a special type of cobordism. So we say they are concordant. And so what I want to leave you with, where I come in and where Dr. Bosman comes in, is that the set of knots where 2 knots are the same if they are concordant to each other forms the knot concordance group. The group operation is a little more complicated. So I'm going to say, if you want to know what that is, ask Dr. Bosman. He also has some really wonderful knot theory videos that he's made on YouTube. So what is this group? Is it still, is it still just Z? And it turns out, due to work of Jerry Levine in 1969, that the knot concordance group is extremely large. It's ridiculous. We still don't understand it. It's at least as big as an infinite number of copies of the integers, and it uses these algebraic invariants derived from a Seifert surface. And maybe one other thing I want you to take away is that we didn't even understand. So we didn't understand the limitations of these methods. So we didn't understand the limitation of these methods until the 80s. So if you want to look this up, this is something called the algebraic concordance group. It's fun to think about. So maybe what I want to leave you with is where I come in. So here's a couple of theorems. I defined a new algebraic invariant for knots in arbitrary 3 manifolds, which generalize these Milner's higher order linking numbers for links in the 3 sphere. So I have some information on my website if you want to look into that. I had some undergrads do research on this with me over the summer. They wrote a really great introduction to Milner's invariants. I used this new invariant to show that slice and concordant to the simplest knots are different in more complicated 3 manifolds. So slice is like a special version of null cobordant, and I'm not going to get into. And then finally, along with a collaborator at Michigan State, Matt Hedden, I defined a new cobordism group of links inside a specific 3 manifold. So thank you for your time. It's been really wonderful to speak to you.